Okay, so this is part of a pHET simulation. pHET is a website at the University of Colorado in Boulder that has lots of chemistry simulations. This one runs with Java, and so it's a little bit difficult to get to work on all computers. So instead of having you play with this particular one, I'm going to just discuss like how it works a little bit and show you some of the different models. Now, we haven't gone over all these models, so I'll just talk about them briefly. First one, the billiard ball model, was put together by Dalton, and that was around 1800, a long time ago. And so the way he thought about an atom is it doesn't have any parts, it's just this solid round ball. So I'm shooting light at it right now, and you can see the light just bounces off. That's the way he thought of atoms. In the late 1890s, we came up with a new model of the atom. Okay, this one was put together by J.J. Thomson. He thought of atoms as having electrons, so electrons could bounce around inside your atoms, but he didn't know if they, and he knew they were negatively charged, but he couldn't figure out how they were stuck there. So he proposed this plum pudding model where there's like a gooey pudding that's made of weak positive charge, and then there's these little electrons of negative charge sort of stuck in it. And so you can see, kind of would explain a little bit about light coming off, but it doesn't, the only wavelength that comes off is always the same color. Rutherford came along next. He found the nucleus. And so the problem is that he had no explanation for how electrons stayed out of the nucleus. Okay, so you've got these negatively charged particles going around a positive nucleus, so why don't they just spiral down and go kaboom? Okay, so finally, we started to get a model that was sort of mathematically sensible. And this is Bohr's. Now I want to show you the spectrometer. Now you've already seen the line spectra, and I wonder if I can speed this up a little. I guess not. I wanted to show you the line spectra that you're getting from things, light that's hitting these electrons. Now we've got different colored light, which means they have different amounts of energy. Look at the little electron was spinning around. That's the lowest energy level, the ground state. When it gets hit, sometimes it jumps to the second, sometimes it jumps farther. It has all these little different jumps back. And we're starting to accumulate, if we do this, fast enough and long enough, you start to accumulate specific wavelengths of light that are showing up here. All right, so you just got to let it go long enough so you can see all the different jumps. We're also getting some down in the UV range, some in the infrared range. What we're really primarily looking at, though, is between 380 and 780. But they're getting specific lines of visible light that are being emitted. So like I said, if we let this go long enough, I don't know what that will do. If we let it go long enough, though, we can, I can speed it up. Here, let's make it go really fast. And let's see what kind of wavelengths of light we get. You can see we're getting 4. Red, sort of a greenish turquoise, blue, and violet. So if we go fast enough and we get enough transitions, you can see them all. There's, like I said, also some off the IR and infrared end and some of the UV end. So let's slow this back down. If you go super slow, hopefully we can get some light to hit that electron. You can watch what happens. Maybe I'll speed it up just a tiny bit. Oh, you see it jumped. Now watch when it jumps back. Do you see this? That's purple light coming out. All right, it's one of those. So if you see it gets hit and jumps, ooh, it got hit. Where did it go? All the way to the outer ring. Let's see where it jumps back. Oh, it jumped all the way down there and it gave off purple light. And then again, another little beam of light comes out. Now, this model only works, this idea of these fixed rings that are a fixed distance apart only works for the hydrogen atom. I think we're going to skip de Broglie. Schrodinger's actually is the one that actually kind of makes the most sense. Schrodinger's model of the atom is called the wave mechanical model of the atom. And let me speed it up a little bit because we're going a little too slow. Electrons are no longer in orbits, like rings. They're in what are called atomic orbitals, and atomic orbitals have different shapes. So if you look here, you're seeing some different shapes as different things happen, and this over here is showing you the jumps that are happening to get those shapes, and also you get different wavelengths of light that are coming out. If you look carefully, you'll see some. There goes one. They're the ones that are not going in the, there goes one. They're not going in the same direction as everything else. Typically, there goes one off that way. So they're just trying to show you the jumps that correspond to those. Down below, you notice the spectrometer is giving the exact same pattern that was given in, if this was a hydrogen atom, it's giving the exact same pattern that Bohr's model gave. So you're going to get exactly the same wavelengths because the math works out the same. It's just that Schrodinger's equations work not only for the hydrogen atom, they work for all atoms. So whatever bands you would get that you observe down here can be predicted mathematically using Schrodinger's equations. And so what that means is that since we've never found any exceptions, Schrodinger's model probably does accurately account for how electrons are organized inside atoms. And I think that's